In section 4.6, the main concept was this idea of a couple, which is something that would cause pure rotation. So you had two forces equal and opposite, and they were separated by a distance, and you could replace those essentially with a couple, which is just causing pure rotation. Now, what we want to do in section 4.7 is take and simplify, make a simplification where you could have forces acting at different distance and couples acting on an object where you could take them all, sum them together, and come up with a single force and a single couple acting on the system itself or the object itself. Okay, let's think about that first. Let's think about this application to kind of give you an idea. Now, looking at these four different diagrams, we can think about the different forces that are acting here. Now, if we look at the first one up on the left-hand side and we make a comparison from this one and the one on its right, we see that as far as this point B is concerned, a force, this force F acting at point A is essentially the same as a force that would be acting at point B. Both of them would cause, from the hand's perspective, causing a net force to try to pull the hand out, okay, or pull itself out of the hand. The second one, the second example, is if we look at a force acting at a point A, and now this is not a force that's acting straight through the point, but acting at a distance at 90 degrees relative to the hand, we can see that this would cause a couple of things. One, it's causing a force, a net force, to try to push the hand down. And the second one, since it's acting at a distance, it's causing it to try to rotate the hand. Okay? So what we can end up doing is we can actually replace this force with an equivalent force acting straight down at the hand and a couple moment, which is causing rotation. Okay? So that's the main point of this, is taking all the forces, any couple moments that cause pure rotation, having them all act at a single point, and what we can have is a resultant force acting at that point and a moment acting at that point, or moment couple acting at that point, which takes into account the rotation. Okay, so here we go. Another one. All right. So basic idea, so let's say this beam, you have all of these, and you're interested in seeing kind of what's happening at point O due to all the forces acting here, forces and moments acting at other points on this beam. What you can do is you can actually come up with an equivalent, see where you have a resultant force trying to pull, like this, in this case, point O, or the origin, trying to pull it away, plus you have a moment acting at that same point. And that's really essentially all we're going to do in this section, is to actually make the equivalence of this. Okay. So if you think about it, here's just a general object having some forces acting on it, and a moment, or a couple acting at some place on this object. Of course, if it's a couple, essentially that means this is acting anywhere on the object. And what you can do is you can actually take these, and you notice that if you think about point O here, this one would generate a moment about point O, and this one generate a moment about point O, and they're acting at a distance from O. And you have a moment here, is that what you would end up with is you would end up with, coming up with a force, an equivalent force, a resultant force due to these two force vectors, and then a moment or a couple moment or a resultant moment about point O due to the moment generated by this one, uh, this distance, or this distance vector, R and F, and this one, and a couple. And if you add those together, you would come up with a moment about point O and the force vector all acting in a certain direction. And that's essentially what this is. Okay? Okay. So first part, just sort of conceptually, let's see how it happens so we can look back at that original diagram. So if you think about it, if you were coming up with like some an equivalent forces, you could, let's say you're starting off with a force acting at point A. What you can do is you can think about if you had another force here, and you had a force acting off to the right and one acting off to the left, these two together essentially sum to zero, right? Well, what you can do then is take this one and cancel out this one. If you add this one together with this one, then you can see that um, uh, the final force is just the F acting at the hand. Okay. So uh, when you have when you're taking a force and they're basically acting anywhere along the line of action, it doesn't change any external effect on it. Okay, which kind of makes sense. It's right. What difference does it make if you're pulling over here or the bar is pulling on the hand? Essentially the same effect. Okay, this is so-called a force vector is called a sliding vector. Okay, so internal effect does not depend on where the force is applied. All right, and that's essentially all this is saying. Okay, so we can move its line of action. The second part of this is the moment. Okay. Now, the same thing here, right? If you looked at point B, what's the effect of this force and this force together? So if you took these two and added them together, what do you end up with? Well, essentially at this point, it looks like zero. But what we can see from this is that if I use this force and this force here together, I actually have a couple. I've created a couple here because these two together would just cause pure rotation. Together, you add these two together, it doesn't cause any translation down in the y direction or in the y direction. It would just cause rotation. So what you can do then is just, of course, this is a couple moment. You can actually apply this anywhere along the beam. So use this force and this force together, and that generates a couple, which can be applied anywhere along the beam, which you could apply right here at the hand. So you have a force F acting left over. It's just this one and a couple made by these two forces. Okay. Okay. And the same idea, right? A new couple moment. Couple moment, so-called free vector. It causes pure rotation, so you can apply that anywhere along an object. Okay. All right. So, okay. So just overall, this is what you have, even when it's in 3 dimensions. So what do you do? And this is the other object we looked at. The resultant force is going to be the summation of all the forces. They're vectors, right? So summation of all the force vectors to come up with a resultant force vector. The moments, it's going to be any couples that are associated with this. In this case, in this particular example, we have this. This is our couple moment. And the resultant of the forces or the vectors of the moment vectors about a point. Okay, so the two parts, the couples, any couples that cause pure rotation, and then the moments about whatever point of action point you're looking at and you care about. Okay, and really the idea is that some common point, right, that we're looking at. Okay, all right. Here's another example. So you have two lights. So we're going to look at, in this case, we're going to look at the impact on point O. What does it look like? Well, if you think about it, there's, from point O's perspective, it looks like two weights trying to push this down, right, due to the two weights. And the second part of this is that these two weights, or these two lights, the weights of the traffic lights, are causing rotation about this point. Okay, so if you take these two together, WR, of course, is going to be the weights of these two, and then the rotation about this point is the moment, which is just be D2 times W2 plus W1 times D1. The moment couple about this point is just due to those two. Okay, and so this is all we have. The resultant force acting down, and then the moment W1 D1 plus W2 D2. Okay, and that you could replace this essentially, these two traffic lights here acting along this beam, with a single moment couple acting at this point, point O, and then a weight pushing straight down. Okay. Okay. So let's look at a few examples. The first part of this is that we want to come up with the first one. Okay, we want to come up with equivalent resultant force and couple acting at a point. Okay, in this case, this asking for at point A. Okay. Well, all you really need to do is you're going to start off. The first part is coming up with a resultant force. And the resultant force is just going to be, okay, the y components, which is this, plus the y component of the 50, which is just cosine of 50, cosine of 30 times 50. And then the y component of this, which is just negative, which is just going to be, 4 over 5 times 100. Okay, and that gives you the y components. And then the x components, you're going to have a, 50 pounds times the sine of 30 here. And then 3 over 5 times 100 pounds over here, acting in this direction. Okay, so that would give you the result. So the first part is you come up with all the x and the y components to come up with this resultant force. Okay, once you do that, now you can think about all the couples, or the moments due to this, right? Well, at A, you can see there's a y component here, so it would just be, the moment due to the 3 times 200. And then we have a y component here. And you'll notice that these are counterclockwise. This would cause counterclockwise rotation, so this one is going to be positive, and then this one over here is going to be also be positive. And then this one's going to cause clockwise rotation, which is going to be negative. But we really don't have to worry about the x components, right? Because the x components would pass straight through this point. The forces, if you drew those forces straight through, they would meet straight through here, right? Because they're acting right at this point, right along this line of action of this of the distance vector r, or the vector r, position vector r. Okay, so those would not impact it at all. So you're just going to have a moment due to the y component here, a moment due to the y component of this one, and a moment due to the y component of this one. Okay. Now the last step is there's one other step, which is actually in the next section, 4.8. We'll just take a quick look at this. But this is the idea that, oh yeah, once you have that, you can actually take it one step further and come up with a resultant distance, a force acting at that distance. And then now you have, as far as that, from that point's perspective, is you could replace everything with just a single force at some distance. Okay, so we'll just talk about that for a minute. Okay, first part. Okay, x components. Here's my x components for my force vectors. Here's my y components for the force vectors. And then here's the moments, right? And there's only the y component here, the y component here, and the y component here, which the first two, this one and this one, are both positive because it's counterclockwise rotation. And this one will cause negative rotation because it's clockwise. Okay, so here is the result in the whole thing. So we have an x component, a y component, and a moment. So as far as A is concerned, you're going to have a force vector acting here, and that one you could either, the magnitude is going to be 184 pounds, and you could actually come up with the angle, right, associated with it just by putting the opposite over the adjacent side to come up with an angle, okay, using the inverse tangent. The last step here, you can actually replace those with just a single force acting at a certain location. And the way you would do that is, if you think about it, you're just saying the moment r, the resultant moment about A, is essentially a distance times the force. Well, we already have a force defined, right? If you just take the moment and divide it by the force, you can actually come up with that position. This is actually talked about a bit in section 4.8, which I decided not to cover. But you can replace that. You could take this whole thing, all these forces all together, the moments, any moments that are, or any couples that are generated, and replace all of them with a force, a single force at a certain distance. So this last step is so-called further simplification of the system. Okay, not much to that really. Okay, here's another one. Now we're talking about a plate, and we're going to do the same thing. Okay, so you want to find the x and the y components. Well, not much here. Summation of the forces, they're all acting in the z direction, right? So they're all acting either vertically. So it's simply just adding all these together, and f of I, that's not the unit vector I, that's just an I, just using that as the index. So the resultant force is just going to be the components. It's going to be 100 minus 500 minus 400, and that gives you the resultant forces. And then, of course, the moment, it's going to be the vector r, the position vector, crossed with each of the forces, right? So you expect, yeah, I'm going to have three vectors here, a vector from here to here, a vector from here to here, a vector from here to here, and then I'm going to have a force vector, which is just essentially acting, in the z direction. Okay, so all of those are, so you're going to end up with, of course, some components in the I and some components in the j direction. Okay, and the final point is that once you come up with those, well, it's just as simple as just taking the magnitude of the moment and dividing it by the magnitude of the force to come up with the end result. And then the other one, the y component of that, you can do the same. Okay, so the x and y distances. Okay, so here we go. Here's the force, the equivalent force, which isn't much of anything, right? It's pretty simple, pretty straightforward. They're all in the k direction and the z direction, either positive or negative. Okay, the second part is finding the moment vector. So the first one is 3I to the 100. So if you notice, it's just vector 3, distance of 3, I, and then it's positive x, so that's positive. And then k, it's in the positive z direction, so that's positive. And then we added the moment vector from that one crossed with, here's our position vector, so it's 4 along the x, and it's 4 along the y. And that's where we come up with, and this is just doing the determinant. We did these several times here in class. The last one is just here's my 4j, and then here is my vector that represents. So we need to do cross products on these, right? Because it's three-dimensional. And it's negative 400k because it's going straight down. Okay, so you go through and you come up with, do the cross products of each of these. You'll come up with, here's my components, the I and j components. And now I have a moment vector, which is essentially in the plane, the xy plane. Okay. And then, of course, the last part of this, you can actually go in and just divide by, take the moment ry in the y direction, divide it by the force, and you can actually come up with a position in both that and the x and y. Okay. Now, this last part we're not going to cover because I decided to leave out 4.8. We're going to go on to chapter 5 after this. But the last part is essentially just that. You're just doing the y and the x to come up with that position. Okay. All right. The next example. Okay. So this is one of the things, we're going to get into later on is you'll notice that a problem like this, it's a little bit different. You notice that they have different kinds of supports here for this. And we'll talk about that when we talk about equilibrium conditions. But for now, you'll see that this is a so-called pin support and this is a roller support, okay? But what we want to do here is we want to figure out the resultant force and couple acting at point A. Okay, so not really much different here. Okay, and we're going to do the same thing as before. We're going to come up with x and y components of the forces. Okay, and then we're going to find all those moments in A, and then add a moment to find this. Okay. Okay. Oh, we add them to the 1500 newton meters because that's a couple that was defined right here. Okay. Okay. So first part in the x direction, just the x component of this. This one doesn't have an x component, and then the x component of this one. Okay. Then the y. So the y components, we'd have a y component here, y component here, which is just negative 300, and the y component here, right along here, which is just cosine 30 times the 700, and it's negative because it's going down. So all three of these are negative. They're actually, the y component here is negative, this one's negative, and this is negative. So the result is negative. Okay, so here are the forces, the two forces, in the x and the y direction. And then now, so you can come up with a resultant from that. So the end result of this one, you could come up with its magnitude and its angle associated with it. Here's in the rectangular form, and here is in polar notation where you have a magnitude and an angle. Okay, so not too hard. This is nothing different than what we did in the past. You got your opposite side over the adjacent side here, and do the inverse tangent of that. Okay. The next part is that the moment about RA, okay, and the 1500 here is that couple, right? We're going to add that in to the end. This This, of course, is a couple. A couple is translated anywhere along the object. It's pure rotation, so you always have to include that in when you're coming up with a resultant moment about any point. Okay. So first one is sine of 60 here. Okay. So it's the sine, so it's the side that's opposite. So it's this side right here, or this side if you want to think about it, and it's acting at 2 meters, and that's um, we have to think about this. Oh, notice the notation here. The notation here is he defined this as positive going in the um, clockwise rotation. Um, Typically, we don't do that. Typically, we would say it as being positive or negative. But just following this notation, if you define this being as the positive, then of course this one follows this notation. This is positive. This one results in a positive also, and this one results in a positive, and this one results in a positive also. Okay. In general, typically we would write it as, this saying that the way the author did it here, you have different ways of identifying it. Is just saying that, yeah, it's 9,535 Newton meters in this direction. Okay, going in this direction, right? Typically, we would define it and say that it's counterclockwise. I'm sorry, it's clockwise, so it would be negative. But as long as you're clear, like in this case, it's very clear. Yeah, it's this, and this is the um, rotation about point A that this would cause. Okay. Okay. So here's another one. This is a 3D problem. It's a little bit more involved, but you'll notice just looking at this problem, you'll see 100 Newton meters. Um, that's a couple acting along the perpendicular to this, so it's in the XY plane. Here's another one that's causing rotation about this. And you can actually, you could write it like this or just think about it. Well, it's a vector right in the z direction, so we just include it as a vector, 100 Newton meters K. And then this one is actually in the same direction as this, so we have to include that as part of the vector. Okay, so you'll see that it's a little bit different. Okay, so we have some things. Forces in couple moments are applied to the pipe. We want to find equivalent resultant force in couple moment at point O. Okay. So same story, we're going to we need to do the cross products. We have some couples here. We have this couple and this couple we have to consider. So that's in the couple part. And then the cross products of any forces acting. So we have some forces here. I have a force here acting. I have another force here acting. And then I have another one here. And you're going to find this one. Oh, this force is acting straight through that point. So there's actually no couple associated with it. So just from looking at the diagram, we would expect, okay, so I'm going to have 1, 2, 3 force vectors, right? And this one looks like, oh, well, it's going to have a z component and an x component. This one is just going to be y, and this one is just going to be purely z. But you're going to expect, this is going to have 2 components. This one is going to have 1. This is going to have 1. So we're going to have 4 components or 4 forces or 4 component vectors as part of the force. And the second one is the moment vector. We're going to have a couple here, some moment due to this. So I'm going to have 4 of those also. Okay. Okay. So here we go. So first one, F1. Oh, that's just K going straight up. No problem. F2. Now in this case, F2 is this one. It's acting down. And you can think about, there's really there's no Y component with this one. So you can think about this. So you can come up with a adjacent component, and then you can come up with a opposite component opposite of this angle, and you can come up with a component that's in the z direction and the x direction. Okay, so the adjacent component is just this times cosine 45, which is going to be the same anyways, and then minus sine of 45 because it's going down in the z direction. Okay, so those are your components for the second force. That's F2. F3 is purely just acting in the y direction. So by itself, it's just going to be, 100Jn. Okay, so you can sum all these together and come up with a vector for those. Okay, the second part are the r's, right, where you actually have the position vectors relative to O. Okay, so the first one is, 0.5 here, I. That's our first one. The second one, R2, is going to be at 0.5 and 0.6, so it's acting right here, and it's right along the J axis. And then R3, hmm, R3 is going to be 1.9. So it's this, and this. And that's acting at point C, which really, that one doesn't matter for us. Okay. Okay. So then we have a couple moment.